Okay. So I think we'll make a start because it's 5 past. So last time we talked about simulation, and we sort of went from the world of machine learning and these models where we could express our uncertainties in tractable forms, which Carl Henrik had been talking about, to a world where we're writing computational models very often of what we think the world looks like. And that could be physical systems with understanding of physics, or that could be more, I'm an expert in supply chain, or I'm an expert in Formula One, and I know what happens in the races. One of the things we sort of talked about is levels of abstraction and how different models have different levels of abstraction. And some models are really trying to be very close to the physical world, like models for climate or weather. But other models, like those supply chain systems, can be really capturing something that's quite distant from the underlying physics. So today we're sort of going to try and bring back in the notion of emulation and machine learning models in that picture. So I launched yesterday's lecture by talking about the need for computational power. We used the game of life from Conway to sort of show that even in a world where we understand everything, where the data is, what the physical laws are, there's still uncertainty in what those emergent properties might be. And the trick in surrogate modeling, or emulation, as I tend to call it, so the words, you'll see the different words being used. Emulation I use because there was a really strong group in this in Sheffield led by Tony O'Hagan, and they tend to use emulation, but it's also called surrogate modeling. So we use statistical or machine learning models to learn regularities in those emergent phenomena. So the trick is that you run your computational model, but because there's sort of effects in the real world, like central limit theorem and all these sort of things, what you often find is you get these emergent phenomena, like a hurricane in the sort of weather systems. And the idea here is, well, those emergent phenomena themselves are sort of exhibiting some regularities that, rather than producing from first principles, what we're going to try and do is we'll reconstruct them with a machine learning model, so with a Gaussian process. And that's the sort of basic idea in emulation. So if we think about different types of simulation, then there's a few different ways in which people simulate things. So very common one is differential equations. So physical models of climate are often based on Navier-Stokes equations, but that's when it's very close to what they're. So there you're sort of including your real physical understanding about things like conservation of mass across cells and so on and so forth. But they can also be abstracted. So an example that I'll go through a little bit is sort of epidemiological models. There you start using these differential equation models, but you know, it's about an abstracted thing about transmission of a virus. It's not actually measuring, you know, at a very precise level the interaction of that virus with how it goes into your system. It's just, well, loosely speaking, we think that this can operate like a differential equation. Another very, very big class is discrete event simulations. So I always think, like, the game of life is a discrete event simulation. You're going through some sort of set of turns, and in each set of turns, you allow certain things to happen. Formula One simulation is often done as a discrete event simulation. So often the lap is either broken up into sectors, and then you look at each sector and you say something happened in this sector, or you could even treat the whole lap as an event. But then there's also, so those are the time-based discrete event simulations, but then there's also event-based simulations. And actually, if you're interested in this, any chemists here? So if you work in chemistry, there's something called the Gillespie algorithm. And in the Gillespie algorithm, what you do is, it's an event-based thing. So you keep track of all your molecules in your system, and then you look at, you use the fact that you've got Poisson statistics in terms of when they're likely to collide to sample when you expect the next event to happen. So it's not a sort of discrete, like it happens, you know, every constant turn. It's like, oh, the next thing that's going to happen, we'll sample when that occurs, and that's going to be a collision between these molecules, and we'll move the whole simulation on to that point. So they're often much more efficient, but harder to write in practice. But the Gillespie algorithm for sort of chemical simulations, when you've got small numbers, you're trying to do stochastic systems is an example of that. And it's a very old example that was implemented on the earliest computers. And then the other key point we were talking about is the fidelity of the simulation and how much, and this is one of the things I think about this course where it's so important. And I'm so pleased we've got people from other departments in here, because really the objective we have is to teach people who are domain experts how to use these techniques, because it's often an art to decide what the fidelity of the simulation should be. So the example we talked about last time is the difference between, saying, a strategy simulation where we're thinking about probability of overtake as being just a function of the difference between the top speed of two different cars, and what's actually going on if you were to do an aerodynamic simulation of that at the low level, which is how they design the cars. These are clearly, you know, they're modeling the same thing, but at a totally different level of fidelity. So in a very real sense, what's going on there is the domain expert is doing that emulation themselves. They're doing that abstraction themselves. They're saying, oh, well, instead of thinking about how this car is going to interact with the other one, I'm just going to emulate that with a little function that I'll create. So I think for me, an emulation is quite widely used, but this shows the potential of how it could be much more widely used than it is. You start thinking, well, what if we could start doing things like automatically deciding when to do that? So start, you know, maybe like, okay, in an extreme example, from a really high fidelity simulation, and start saying, well, actually, I can just replace this big aerodynamic simulation with a single function, but the function could be of this form. A lot of people were asking afterwards, well, why would you only include certain variables? And all those questions are sort of a function of the problem you're trying to address. So let's just look at that epidemiology example again, just as an example to have in your head. So in an epidemiological model, you've got these different compartments of infected people, and you sort of define differential equations about how these different compartments interact with each other. And that isn't really representing what's happening in the underlying system. And you even get odd things here, like there are two, the details of this example are in the notes. But there's two compartments for infected. And as I was saying last time, there's two compartments for infected, because if you just run these differential equations without thinking about it, what you're creating is I think it's true to say that implicitly what you're saying is infection times are exponentially distributed. And we know for COVID-19 that they're not exponentially distributed. So what's going on here, it's not explained in Thomas's blog post. And I think this is my inference about why they do this. So you'd need to double check with an epidemiologist. But this would make sense to me, is you get these two infected compartments, because in order to get the statistics of the infection closer to the reality of the infection, they assume that you go through two stages of infection. And that means that instead of being exponentially distributed in your infection times are implicitly, I should also say there's a deterministic model, but it's a deterministic model that is derived from statistics of what you expect to happen at large scale when people are interacting. And it's those statistics I'm talking about. The implicit assumption would be that you've got the sum of two exponentially distributed models, right? And if those exponentially distributed times for infection, and if those exponential distributions have the same scale factor, you get actually a gamma distribution for the infected time. So I think that's what's going on there. But it's all operating at this level of high abstraction. This is just what we observe in practice, that people seem to have an infection time of that amount. So that's what we introduce in the model. And then if you go through the example in the notebook, which is in Google Colab, you can run these simulations yourselves. And to run these simulations, I mean, there's other things going on that you're doing Runge-Kutta underneath to solve the differential equation. So the model is defined through a set of differential equations that are then solved through Runge-Kutta. This is fairly quick to run. One of the exercises at the end of the notebook that you can try if you like is to do things like, so here what Thomas was exploring, and this was in the early days of the pandemic, right at the beginning of the pandemic, he was just trying to illustrate what happens to your model of how many infected people you get with different intervention times for lockdown, with some assumption about what things look like under lockdown. So you get some sort of function of your timing of lockdown, and then you're getting an output, which is, somehow your maximum number of infections or maximum number of deaths or something like that. So what you can do here, if you like, or you should be able to do at the end of this thing if you're interested, is you could build the emulation where you map from those parameters to the maximum peak number of infected thing, which might be what you're trying to decide about at the end of the day. Now, in this case, this is a fast running simulation, so you probably wouldn't do that in practice, but you'll get the general idea. So there's a few more plots on there. So when we think about those simulations, what we typically find is that we'll split the variables that we're interested into. These are groups that the way I see it. So maybe other people use different terminology, but you've got state variables, parameters, and results. So in that herd immunity simulation, you have state variables which represent those who are susceptible to infection. That's the S that you'll see in there. Those that have been exposed, those that are infectious, and those that have recovered, right? So those are the state variables, and they're changing all over time. So the state variables very often are things that are moving up and down with time. So it might, you know, in Formula One, it might be the sort of position of the car in the race. Then you've got things like parameters. I always think of parameters as things that are sort of static for the whole system. Sometimes parameters vary with time, and there's sometimes an overlap between these two, but broadly speaking, you often find that there's this separation between the two. And in this case, the parameters of the model are the reproduction number, which if you look deeply into SAGE minutes, you'll see was misestimated at the beginning of the pandemic, which is what led people to say we were 4 weeks behind Italy when we were only 2 weeks behind Italy. The expected length of infection, and the lockdown timings is to sort of study the interventions that are going on in this case. And then you get the results, for example, the total number of deaths you expect, or the total number of infections you expect, whether you're looking, are you worried more about your hospitals being overwhelmed or the number of dead or whichever. And so what you can see here is actually what you typically would do in an emulation is your inputs of your Gaussian process might well be the parameters, and the outputs are going to be some form of result. Yeah. So you wouldn't necessarily, in this case, the state variables are just things that are going on in the background. They're not your inputs. And what you're going to do with your surrogate modeling is you would end up sort of training a Gaussian process to map from the parameters that you try to the results that you try, right? And in this case, if you're confident about reproduction number, then you might just keep the reproduction number fixed, the expected length of infection fixed, and then you could predict, you could move the lockdown timings to see what the result is. And you'll get a very simple result that, you know, infections go up the later you lock down. But you could then, as we'll see as we go through the course, you can start doing things like sensitivity analysis. How sensitive is this to our assumptions about what the reproduction number is, for example? Yeah. So the idea is basically that we use an emulator to map from the parameters to the total number of deaths or the total infected. And we treat the parameters and results of the simulator as inputs and outputs to that emulator. And that's basically what's going to go on in surrogate modeling. Now, I want to just talk about a third type of simulation, because it's sort of funny. When I went to Amazon, we talk about simulation a lot. And at some point, you know, I don't know, like a year in, you realize, oh, they mean something different when you say simulation to what we mean. And very often in a computer systems context, what people say simulation is they actually mean back testing or counterfactual testing of code bases. So it's sort of an odd one, because it's, in some sense, it's not a simulation. It's not a simulation in that you're actually running your live and active code base, but you're doing it by changing the inputs. So you're doing a sort of like, what would have happened if we had put this input in instead? So that's the notion of a simulation. It's not the inputs that are coming in live from your actual production systems. It's you're going back to those production systems and changing an input. So I just wanted to say a little bit about that type of system. So I've included some fun videos. You don't have to, there's a sort of in Amazon joke in this one, in that this, I think this book here was the first book to be sold on Amazon. And this is a team I work with. This is Devesh and Lou, who are the vice presidents inside the team. Devesh is now actually CPO, CTO of Deliveroo. He's moved, and Lou also moved out of this team. But this was the supply chain optimization team when I was there. And this little video tells a little bit about what they do in a sort of way that is supposed to attract you, to make you want to work for Amazon. So there's a friendly orange character that wears a kilt. But basically the problem that we were trying to solve, and we're hopeful that Jordan from that team, who, you know, there was some people, you know, I think whenever you're in a circumstance working in large teams, and I would say this is true of the pandemic and also true of also working in Amazon, there are some individuals that stand out that really have an effect over and above others. And hopefully one of those individuals, Jordan, will be giving one of the talks about the more details of this system, if we can get his permission sorted and everything in the sort of last part. But this is broadly speaking what's going on in the system, that you have a demand forecast, you've got a supply forecast, and then you've got a cost basis. And then you look at your stock and you've got some availability of stock and you make purchase orders. Now, within this system, the demand forecast is typically actually a machine learning model itself. So based on how often people are looking at certain pages within the Amazon system, the supply forecast is often we would call that a vendor lead time forecast. So it's knowing who can supply these objects to you and how long they typically take, like whether they're likely to have things in stock and how long they'll take to deliver, right? And then you've got a cost basis, which is how much it costs you to store these items in your network, how much it costs to transport those items, how much there's also a really interesting number, which is what is the value to the consumer that you stock that item? So there's a sense in which some items are just useful for people to have on the site, and they try and estimate that as well. And then so you combine all these things together, and that's actually done with an operations research model. So a lot of this type of work is done with OR, and it always strikes me that you can tell how far behind machine learning is from an AI from where it claims to be by the lack of interaction between OR and machine learning. Because in real world, in practice, in manufacturing, most of these things are done by operations research. Yet if you sort of hear, if you go to the big ML conferences, you rarely see people talking about comparing their work to how it would be done in an OR sense. I always think that OR is like the machine learning of the 1940s. You know, in the 1940s, people worked out all these mathematical techniques, linear programming for optimizing systems to do with the fact that there was a big war going on. And that really became a big field and is still a big field. So it sort of always interests me how little interaction there is between machine learning and AI and OR. But yeah, so this was all done by OR models in the center. And a lot of the people in the team were OR people. So I've included, if you're interested more in the details, there's a massive forecasting team. This is Jenny Freshwater, Ping Zhu, and Dean Foster, who were all senior people, tech people, and leaders in the forecasting team. You can watch a little video here of Jenny talking about the whole system at a big Amazon event, if you're interested. It's not supposed to be an advert for Amazon. I'm just trying to give you a sense of how these things happen when they're going on a scale, and the number of people that are involved in doing these things. So that team was only about forecasting what the demand was. This was the team I was in. This is Piyush, Raman, Salal, and Narayan. And these were different experts and managers in the automated buying system itself. Narayan was kind of my favorite. Well, they all were lovely, but Narayan's a long-term supply chain expert who had this wonderful voice that sounded like God. And we got really along together because we were both remote. So we were always sitting in these meetings pre-pandemic, sort of trying to interrupt. And Narayan just eventually with just this godlike voice would appear in the room. It was brilliant. So those were all the sort of domain experts who understood how supply chain works and what can go wrong with it. And it's kind of really interesting, you know, now how our supply chain internationally is kind of going a bit funny, trying to deal with all that. And then that team, that last team there, then makes the buying decision itself and sends out purchase orders. So what I wanted to sort of talk about in the sense of that is how that tends to emerge in software systems. And I want to relate it to what went on with the Amazon web server. So these two people here, Charlie Bell, who's just left Amazon, gone to Microsoft. He was the technical lead of AWS, and Peter Voschel, who was the sort of first, he was the sort of lead engineer who built the AWS system. And I want to say a little bit about why what they did was innovative. So what I'm showing you here is all of these systems placed in a piece of software. So a single big piece of software that runs everything. And we can think of it, imagine that. So I've got one big executable on my Windows machine. I know this is very out of date. And each of these systems are in that, and they're sort of all calling each other. Now that's called a monolithic system. And Charlie used to run Obidos, which was Amazon's monolithic system for running its web server. Like going right back from the beginning, 1994, up until about, I think, 2006, we're talking about, a big piece of code that was running on these things. And what they found, and Charlie, I talked to Charlie about this, is a lot of what he had to do was just keep, you know, it was firefighting because the demand on the system's going up and up and up. And they're having to maintain this system to stop the whole thing crashing as the number of users is going up. And they realized that this wasn't scalable and sustainable. And so Peter, with a team, moved up the hill. And what they worked on is the sort of modern way that we view these things, which is a service-oriented architecture. So the way that you build a modern software system here is, instead of having that, and I'm showing it for the supply chain because we're talking about supply chain, but the idea would have been for the web service originally, right? That instead of having this monolithic piece of code, what you have is you have a number of individual services. So you have one service, which is the demand forecast, and that's called by another. Well, in this case, I'm showing the path through the system. So in order to make the purchase order, you need to combine these three things. So these are supposed to be showing joins. This is a way that myself and some of my team view this. You need to join the demand forecast for an item, for a particular item in the supply chain, to a supply forecast for that item. And then you need to find the cost predictions, and then you need to combine those to make your purchase order. And that happens for every item every week in the supply chain across Amazon, right? So what I'm trying to show here, though, that these are decoupled, though. So actually they depend on many more inputs than this, but I'm trying to show the join that you require, the multiple joins that you require to get your purchase order. But the key point is that these pieces of software now stand alone and are owned by a small team. So in Amazon, they used to call these 2 pizza teams, and that the implication was they're sort of that you can feed the team with 2 pizzas. Now, in Italy, that would be 4 people, but in America, that's like 12 people, because Italian pizzas are a sensible size and Americans are very large. So yeah, the teams might be up to 12, but they're typically sort of 6 to 12, that sort of thing. And the point is that you own this service, you own its outputs, and you call other services for the inputs. And these calls are made using what's called REST APIs. So the HTML calls on these RESTful interfaces. It's funny because I was at the management level, I'm quite good at sort of talking about this. Don't ask me the details of what's in a REST API header, because that would expose me. But I can say this stuff in management meetings. So these REST APIs sort of would call and join these things together. And each of these things has a certain number of specific inputs and a certain number of specific outputs. And really, that was the work Peter was doing on a hill in Seattle, while Charlie was firefighting, trying to keep the sort of monolithic service running until they switched it all across. And that's the launch of AWS, because the way you do this is you now have scalability, you now have the ability to put these on different machines, you write these in such a way that this decomposition can scale to run whatever level you want. And so the other really clever bit about it is, once they've done this, they then launch this as a service for everyone to use. And that's kind of the foundation of cloud computing, right? How does that relate to the sort of things that we're interested in? So here, I'm trying to sort of show a climate model. And again, I'm not an expert. I'll do the management level climate modeling discussion. So in most climate models, as I understand it, you have what I think of as 4 particular components. You've got an atmospheric model, which is saying what's going on in the atmosphere in terms of chemical equations. You've got an ocean model, which talks about what's going on in the oceans. You've got a land model, and then you may have a human behavior model. Now, each of these models, you're going to see, if you're going to be doing it over time, you'll be making decisions separately about how to abstract them. And one of the things that happens in climate modeling is there's teams that are expert in each of these domains, and then these things need to be joined together and calibrated, which is a bit of a headache in itself. So that's the sort of thing that we've got. You can go across the university and you can find, like, I think in chemistry, they do a lot on the atmosphere, different departments that operate different part of this modeling. So conceptually, this is one thing I think, and if you, so I hesitate to say digital twins, but everyone's saying digital twins. I don't really know what they're supposed to be, because everything I'm talking about already exists, and it seems to be rather similar to what people are talking about in digital twins. But conceptually, I think one thing that we need to do with such models is the type of decomposition that we just talked about going on between from the monolithic web service to the service-oriented architecture. And it's interesting talking to people that I think people have a sense that that should happen, but that's not something that's happening at the moment. But conceptually, you can imagine the same thing, that you get these monolithic. Here, it isn't monolithic at this level, actually. I mean, these are properly joined as services at this level. But if you were to go into these atmospheric models, you would find, I think, some monolithic code bases. And we need to sort of do the same thing and go to these service-oriented architectures. And the reason I like that is because I tend to think about that type of thing quite a lot, that decomposition of a problem into its component parts, which is done from a software engineering because of the need. It's called separation of concerns, right? It goes all the way back to people who tried to study, why is it when you put more people on a software engineering task, it takes longer? Because there's a communication overhead, and the communication overhead slows everything up. So if you decompose it into these parts, it's the human communication overhead you're worried about, then that reduces these communication overheads. If you give everyone, you work on this, you work on that, you work on this. And that separation of concerns thing you can see is naturally happening in the scientific domains as well. But a really interesting question is, if you have separated into the different parts, who cares about the whole? And actually, I'm sort of pushing my research agenda here. To me, emulation is a real way of helping with that, because you need to stick these parts together in a way that's calibrated and matches reality in some way. And I see emulation. The reason this course exists is because I think that emulation is going to be absolutely critical in doing that just across a number of domains. And that's why we're sort of teaching it. So there's that whole sort of process of that you've got these components and you're going around doing experiment, analyze, design. So you're sort of running these simulations. But as part of this, you're going to be sort of potentially deploying emulations to cover the bit that you care less about, or the bit that you'd like to abstract. So, you know, equivalent to going from the full aerodynamic model to, we just need a model of overtaking here. We don't really care about what the molecules are doing in that model. That whole process now is something that's going on, I think, with any of these systems. I mean, this was something that in Amazon, my team was really pushing this in the supply chain. And this is just ripping off a Bezos statement. He said, because he says this thing about, we don't know what the world will look like in 10 years time or 5 years time or something, but we know people won't want to pay more for stuff. They won't want it slower, and they won't want a restricted number of things to buy. That's the way they view the Amazon website. So we've just converted that into science. We don't know what science we'll want to do in 5 years time, but we won't want slower experiments. We won't want more expensive experiments, and we won't want a narrow selection of experiments. So very much at the core of what I'm saying, why I think emulation is key and will be part of that, is because of the speed thing, right? Now, but the other problem that we're not going to talk about in this course, that is something I worry about a lot, is the challenge I'm not mentioning is, in order to do emulation on that system I showed, what you get, because of the separation of concerns, well, let's do it on this system here, you end up needing to talk to every single team and how they've connected their software up to everyone else's software. That's not programmatically discoverable. And that's a massive headache for large, complex software systems at the moment. I think it's also a headache for large scale science systems. Okay. So, so to sort of give you a sense of in climate, unfortunately, I keep thinking I need to redo this because it's stolen from the UK Met Office website. But I love this plot because the UK Met Office prides itself on having what do they call it, a universal model, I think. So they've got one kind of, it can't be monolithic. I don't know. I really need to get more details on this because it's a bit kind of extraordinary, that they have one code base that will run across. On the x-axis, we've got forecast lead times, so different time scales. And on the y-axis, we've got different grid lengths, so different spatial scales. And why I really love this plot, I'm not personally sure whether this is a good idea or not. I don't know. It's certainly not the way the Amazon supply chain is run, but it's almost totally the opposite, right? What you see here is different models that they run. And the claim is that these are run on with the same physics, the same underlying sort of subroutine to run the physics, which is kind of fascinating, isn't it? So you're going up to 20 to 100 years here, and here you're down at 48-hour lead times. And here you're going from 1.5 kilometers. I think the new supercomputer will be down to 800-meter grids in the UK. And then you're going up to 300-kilometer grids at the top. So you're sort of farting at the top right there, which I think is disused. I think the color gray means retired. You see a retired model that was forecasting out 100 years in 300-kilometer grids. So this is another way in which fidelity is coming in, right? So so we're conceptually saying, well, we could replace the underlying simulation with a machine learning model. But actually what goes on in practice in order to get the speed is they reduce the fidelity by increasing grid size and forecasting out further time. So you're going for a much coarser discretization, which is another way of getting approximations. So this is the way, this is the sort of, certainly the model. This is why I'm excited about emulation and surrogate modeling, because what I tend to think of is that you have these different things going on. You've got the real world, and we can acquire data from the real world, and most of machine learning concerns itself with that and fitting the data in the real world. But as you know from this course, we've now got simulators, and we've got different types of simulators which have different fidelities because they're written for different purposes. So we would expect, and these are sort of my lower fidelity simulations, they're smaller. The real world's biggest because it's a high fidelity simulation of itself. And then, we've got a higher fidelity simulation here. And the question is, when you're trying to make a decision about what to do, should we intervene, in a particular industry to reduce carbon dioxide? Should we, or should we buy a certain product, or should we pit stop our car now? All of these things require, you have this different abilities to ask different questions of either your simulator or the real world. But the one thing that's quite hard to do is how do you deal with the fact that they will often be inconsistent? So how do you know which to rely on? So in Formula One, for example, the sort of things get messy when you're doing computational fluids. So the equivalent of this in Formula One would be, this would be like a wind tunnel test here, yeah? Which is a form of simulation. I mean, it's a physical simulation. These would be two different computational fluid dynamics simulations that might make different assumptions about how to handle turbulence, which is difficult to handle, right? So different simulations handle it in different ways. And so you could ask each of them, and then this would be track testing, right? So you can ask each of these things, whether a part that you've put on the car is good or not, right? That's the sort of thing. I've designed a new wing. I want to put it on the car. Is it any good? And the interesting thing in Formula One is they actually, there are regulations that limit the amount of computational fluid dynamics you can do, and the amount of wind tunnel you can do, and the amount of real world testing. So you have a limited budget for each of these. So the question is, well, which of these things do I ask? And the emulation is a way of sort of replacing that simulator with a sort of a mathematical function. So in the Formula One case, you would have to parameterize your wing in a certain way, and then you would have to make a prediction. The prediction, your output, your result of your simulation is something, for some reason they always talk in points of error, and I never really understood what that meant, but I was at the management level, so I didn't really reveal it. So they say, oh, we put this new wing on and we gain 0.3 points. Okay, that's nice for you. So the role of the emulator would be to parameterize that wing in some way and then predict the points of that. But that prediction could be coming from the simulator, right? But then the nice thing you can start imagining doing is you could try and calibrate that simulation within the same emulation. And we'll see this when we look at multi-fidelity emulation later. You try and sort of say, how is that departing from the real world? So what you start doing is building a picture in your machine learning systems, which is not just what the simulation says, but how is this simulation differing from what I see in the real world? So a very typical thing, so this was really fascinating. One of the most important things in aerodynamic simulation for Formula One cars is how fast they go around a very slow speed corner, because slow speed corners tend to precede very long straights. And if you've lost speed at the beginning of the straight, you lose it across the straight. So this has an enormous effect on the performance of the car. And then it was quite kind of interesting that it turns out that this higher fidelity simulation can't replicate the conditions of the wind bending around, because it's like a 30-degree turn, and you have to bend your wind around a 30-degree turn, and the wind tunnels only go to like 10-degree turns. So interestingly, you're in a zone where the bit you care most about, you cannot simulate in your most accurate simulation. So you're going to have to rely on, you're extrapolating in that region, basically. So you have to rely on the simulators to extrapolate. But if you can learn from limited real-world data, combined with lots of simulation data, and then you combine that with your wind tunnel testing, and you can then have potentially this emulator arbitrate between the three. Now, there's something a bit odd about that, because in order for that to do it well, it almost has to be a better model than all the real world, the simulation. I don't know, the model capacity seems to be enormous, doesn't it? But the point is, it's not trying to reconstruct everything the simulator can do. It's just reconstructing a particular question. Yeah. And it may be reconstructing that particular question within a particular domain. So the reason you can potentially get away with an emulation that is less rich in terms of its representational ability, clearly, than this whole simulation might be, is because you'll be asking a restricted question of this emulator. So the thing I want to make it clear is there's no like Lord of the Rings emulator, one emulator to rule them all. You would need to deploy these multiple times for different questions. And that was one of the sort of challenges we always had in the Amazon framework, is what you really wanted is a big system for being able to automatically deploy these emulators on demand. And we did manage to do that with Prime Air, but we never managed to do that in the supply chain because there's that much more code. And I think they're still working on doing that, actually. I see adverts occasionally for jobs that imply that's the case. So the last thing I want to talk about in the next sort of 10 minutes is, I think the thing I really like about this course is we've got such diversity of people auditing and on the master's courses. And the aim is that you can, the really nice thing is that there's Carl Rasmussen's course on Gaussian processes, which is going into the sort of details of how those things work. And you can definitely study that. And I find that very interesting. But you can also do a lot of what we're doing without understanding all those details. I mean, Carl's already done a great job on sort of showing you the essence and showing you the sort of things you should do with Gaussian processes to get a sort of intuitive understanding of them. But what I'm going to suggest is that you use this software we created called GPy, which is a Gaussian process framework in Python, to do your emulation. And, you know, if you've got time, put it in as an additional exercise on the worksheet. We're not marking these exercises, so you can do what you like with them. But I just thought it might be interesting if, having heard the lecture today, you just have a go at emulating the herd immunity simulation with a Gaussian process. I should warn you, I haven't done it myself, so it might not work out very well, but it was just a thought I had sort of an hour before the lecture. And I don't mean to do it to sort of like get a full emulation, just to sort of distill what we're saying and what the inputs and the outputs would be and how the emulator is operating relative to the simulator. I'll probably try and make a tidier job of that suggestion for next year. So this software is BSD licensed software based. That means it can be used and incorporated commercially by anyone. And it's sort of, well, actually, I would probably take that. When we first wrote it, it was quite innovative that we were doing things in Python. It is no longer, but it's been around a long time. And what you have at the end of the lecture notes today is just a quick tutorial on how to use GPy that was written by James Hentzman and Nicolas Durand, both of whom, James is now in Amazon doing some, I presume, doing some of the things I've just talked about. Nicola is at the local startup Second Mind, but when they wrote this, they were both up in Sheffield with me, and they're both major contributors to the GPy framework, and they've written other software frameworks since. But just to sort of give you an idea of what we do in that framework is, this is a covariance function mathematically, and then this is the code for constructing that covariance function in Python. So you've got a length scale, and we call the variance alpha here. You see variance is equal to alpha. So these things are trying to map onto the way that we talk about them. So the code's quite readable. And that's like, and then you've got an object that is implementing that covariance function. So then there's a range of covariance functions provided for you, a number of things that are commonly used, like the Matern family of covariance functions. I mean, there's a bunch of other things, and there's instructions like how you write your own covariance function. And the sort of thing that you can do very easily, code's running off to the right here, but the important line is this one, is you can do things like, the nice thing about Gaussian processes is the sum of two functions that are distributed as a Gaussian process is also a Gaussian process, and the covariance function is the sum of the underlying functions. So I guess all the frameworks do this now, but GPy was this sort of original one, I think. So there's these nice things like you can create a new covariance function by summing two other covariance functions. So here you get this one Gaussian process covariance being added to this Matern 5.2. The Matern 5.2, by the way, is it has functions that are less smooth than the RBF. Everything you've seen so far has basically been RBF covariance functions. And yeah, you can also multiply. So it's less it's not the case that two Gaussian processes multiplied together is another Gaussian process, but you can multiply covariance functions, and that leads to another valid covariance function. So there's just a sort of, in the tutorial, there's just some ability to play with that. And if you want to sort of see more about kernel function design, this is Nicola. We run this Gaussian process summer school. This is the 2016 edition. You can probably find more recent times of him giving this talk, just going through what these different covariance functions do and why you might be interested in them. I think it's about an hour-long talk. I mean, you don't have to do all this by next time. I'm just giving you, it's like 3 hours worth of video on there already. Just giving you pointers for those things you might be interested in. And then the sort of the task you're sort of set up to do is in the notes is just do a regression on a data set like this, and it gives you the code so that you can see how it's being done. And then that's before you fit the parameters of the covariance function, and then that's after you fit the parameters of the covariance function. That's the fit you should get. And then there's a final example, which is a small emulation example where the code again is written for you, where you compute the expected output over a certain range of a particular test function called the Brannin function. And the point in this one is that you, instead of computing the expectation by the expectation of the Brannin function directly, you use Monte Carlo samples to replace that. So once again, it's one of those examples where computing the Brannin function takes no time. It's probably quicker than computing a Gaussian process. So the game you're supposed to be pretending in your head is that that's some fancy simulation that might take hours or days to run, and you're using a shortcut by using the Gaussian process to do that. So almost all the simulations we'll use with you are of that category, because obviously you don't want to spend hours doing your work. So this is like the fit that you'll get of the Gaussian process to this Brannin function if you choose these input points, and it's all sort of laid out in the tutorial for you. So I think what I'm going to do is stop there and sort of take questions for the next 10 minutes or so, and because I think, you know, I'm covering quite a lot, and I know it's a diverse audience, and I sort of think different people will be interested in different parts. The last bit is something I'll probably move to the lecture on sensitivity analysis, or MUKit. And the last thing here, by the way, is this is the other thing that you learn in a company is if you're trying to persuade your vice president, some of the pictures you've seen up there, that emulation is a good idea, then having a toy example of how to do it is very, very useful. So we had a student, Leah Hurst, and Cliff McCullum. I don't have Leah's picture, unfortunately, but Cliff McCullum together, a student, Leah, was a software engineering intern from the University of Dundee who came to work with us, and she built this sort of web interface to play with emulation and Bayesian optimization that is targeted at senior managers. So if you believe yourself to be a senior manager type, you can go and play with that and see how it feels to be. I don't know, not sure if any of them ever used it, but I really liked it. It's sort of, here it's a taxi simulation of how many taxis should you deploy, and it's all done with sort of little visual effects and everything else to keep the managers happy. And you can get things like where you're exploring the profit you have as you deploy different numbers. Managers like profit, you know, that's important. As you deploy different numbers of taxis, and you're learning how to maximize profit. And that's the sort of thing that Carl Henrik, how we do that in practice, we'll talk about next time. So from today, we've done a few things. We've characterized different types, or we summarized our characterization of different types of simulations we might use. Physical laws, discrete event simulations, production software systems. I should probably re-emphasize the whole notion of abstraction that's always going on in these simulations that allows us to speed things up. And we've introduced the notion of emulation to replace simulation, and we've overviewed the GPy software. So next time, I guess it's based in optimization, isn't it? So we'll take that to the next level on, is that Tuesday, isn't it? Where Carl Henrik will show how you do this sort of mathematically for the particular case of that I just showed here, which is I want to maximize profit. What's the right number of taxis? But we'll stop there and see if there's any questions. And before we do that, I'm just going to stop the recording.